All right, this is what Newton did. He called the derivative, or he wrote the derivative this way. F with a little tick mark. It's called a prime symbol. And when he wanted to indicate derivative, he made that little mark. Okay, he called it a prime. And his formula was the limit one that we've been working on. So the limit of x plus h, f of x plus h, minus f of x all over h. So he was working on how do you find the slope of something curved. Okay, that was what Newton was, and this was how he wrote his ideas. He finally, came up with it in this form. Leibniz is working on the same thing. How do you find the slope of a curve? And Leibniz wrote it this way. He used the letter D in front of the F to stand for derivative. Okay, so Newton wrote F prime to mean derivative. Leibniz wrote df to mean derivative of the function. And then he put dx to show that x is the variable that he was using, whereas Newton used parentheses. So it's different notation, but they were both meaning the same thing. So Leibniz also had limit. He had f of b minus f of a over b minus a. Now we've talked about this before. In Newton's idea, he was having h, which was the separation between the points on a curve. H was approaching 0 to be very, very small. What would Leibniz have had, how would he have written it, to show that the separation between these was very, very small? I've showed you this before. If A and B are the 2 points that you're finding the connection between, the slope between, how would you write to show that they are, yeah? Yep, B approaching A. They are meaning the exact same thing. They both started with 2 separate points. They both assumed that the points were going to be very, 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 very close to each other, so close to each other the separation between them was 0, or that B was approaching A. Those are the same ideas, just one is for Newton and one is Leibniz. So here's how you spell his name, Leibniz. Gottfried was his first name, and then Newton is this other one. If we have time next week, I have a video to show you, a movie to show you about the relationship between these 2 men. So in your book, when they say f prime, please use Newton's definition. When they say df, please use Leibniz's definition. Both will end you up with equivalent answers. And then eventually it'll be like, choose either. Okay, but they'll specify in the book. So we've practiced Newton quite a bit. You've done Newton several times. Let's practice Leibniz and see how his worked. So here's our first example. All right, so find df dx for the following function, 2x squared minus 3x. And so since it was df dx, we'll be using Leibniz's method. All right, so df dx is going to look like this. The limit as b approaches a. So we start out by plugging in b. So that'll be 2b squared minus 3b. And then we subtract, plugging in a, which will be 2a squared plus 3a. And the denominator is b minus a. So we want to clean this up, and we clean it up according to coefficients. That's a slightly different algebra. Instead of trying to match like terms, we're going to match like coefficients. So in other words, you're going to rearrange this when you're doing Leibniz so that the 2b squared and the 2a squared are together because they have like coefficients. And then the minus 3b and the 3a, because they have like coefficients. And let me show you what happens in the algebra when you do that. Factor out the 2 as the common coefficient. What are you left with? B squared minus A squared. What do we call that? What is B squared minus A squared? Difference of squares. All right, B squared minus A squared is the difference of squares. So let's simplify the difference of squares, and we know that it's B minus A, B plus A. Now take out the common coefficient for the back half of the problem. So take out negative 3. And when you take out a negative 3, instead of taking out a positive 3, you'll be left with B minus A. And over the entire denominator, you also have B minus A. So what do you now notice is common in this entire problem? B minus A. Just like in Newton's problem, H was in common, and we got to reduce an H. Here, B minus A is in common, and so we get to reduce that B minus A and that B minus A with the B minus A in the denominator. And so we are left with the limit of B approaching A of 2, B plus A, minus 3, and all of that is in parentheses. After you reduce, you need to have it in parentheses. And now B is approaching A, which means that we can replace B with A. Once you replace it, you don't need to write limit anymore, so it'll be 2 times A plus A minus 3, or 4A minus 3. And you will get the exact same thing if you had done Newton's way. That is called the derivative. That expression represents the slope of the curve at any point on the curve. Any questions about that for Leibniz? Okay, let's try another one for Leibniz. Okay, so again, find d of f, df over dx. For the square root of x. So using Leibniz's df dx means I need to use b approaching a. So the limit as b approaches a, and it's just f of b plugged in first, so that'll be root b, minus f of a plugged in second, which would be root a, over b minus a. This is again the difference of squares. Now you may not see this right away as the difference of squares, but it is. Okay, if we have b squared minus a squared, that's clearly the difference of squares into b minus a, b plus a. Can that same rule apply to just b minus a without the squareds on it? And the answer is yes. You're just separating it into square roots. And so regular b minus a could factor into rad b minus rad a over rad b plus rad a. So this is still the difference of squares. So that was sort of my aside here. So this limit is now equal to, and if I factor the denominator, I'll have rad b minus rad a in my numerator. I'll have rad b minus rad a times rad b plus rad a, and I can reduce again. It's all about factoring into difference of squares. And so we can factor, which means we're left with 1 in the numerator and rad b plus rad a in the denominator, which I can now substitute, and I can drop limit notation as soon as I substitute. So b approaches a, which means I can replace b with a, and I'll have 1 over 2 times the rad of a, which is the expression for the tangent slope of the curve along the original square root function. So remember, the original square root function looks like this. And so if I want to know the slope at any point along that function, if I want to know the slope at 1, I'm going to drop 1 into the derivative, and that will tell me the slope. If I want to know the slope at 2, I'll drop 2 into the derivative, and now I'll know the slope. If I want to know the slope at 3, You just continue dropping different x values into the derivative, and it'll tell you the changing nature of the slope as you go through. So that's how Leibniz did it, which is very similar to Newton. It just all had to do with who published first. Okay, any questions about that one? So you're going to work with both guys' definitions tonight or over the weekend, whenever you do your homework. All right, let's try a couple more. Now you can do either in the following. Write a normal line to the function f of x equals rad x at x is 2. So write a normal line at x is 2. Now this is like your test question. I think it was question 10 on your test. This was the last, and I given you a question, I gave you 10 part A, 10 part B, 10 part C, 10 part D, 10 part E, and 10 part E was finally the normal line. So I was walking you through step by step. Find the derivative. Plug the value in to get the slope. Write the tangent line, write the normal line. Here it's just, I'm not going to give you all that step by step. You're just going to go right to writing the normal line. And so you have to know a couple things to write the normal line. You need to know the point. You need to know what the tangent slope is. And then you need to know the normal slope. And then you can write your line. So to find the slope, I'm going to plug 2 in where? Excuse me, to find the point, I'm going to plug 2 in where? Into the original equation. So my point is 2, rad 2. I'm just plugging it into the original equation. To find the tangent slope, I'm going to plug 2 in where? Into the derivative that I just found in the previous question. Okay, I just found the derivative for the square root of x, which is 1 over 2 rad a. So what will the tangent slope be if I drop 2 into that? 1 over 2 rad 2. What will the normal slope be based on that being the tangent slope? Negative 2 rad 2. So now I can write my normal line. In point slope form will be y minus rad 2, which is y1, the normal slope of 2 rad 2, and then x minus 2. There is no need to distribute. There is no need to clean that up. Leaving it in point slope form is fine, is sufficient. They don't have to do extra work. So you'll see that, and you've seen that before. Okay, last thing. Let's see if this will work. No. Okay, couple. Ooh, that's bad. You can't see that graph paper, can you? Okay. All right. On digital graphs, you're going to now draw the derivative. So for a long time on your homework, you're going to be calculating the derivative, computing it, working out the algebra. But then you're going to be asked to draw it. So let's practice how to draw the derivative. And the word derivative just means draw the slope. Okay, I don't have nice grids here. I'll have to do my best. All right, let's suppose that we have a piecewise function that looks like this, and that's at the number -2. Wow, that's really poor, isn't it? All right, let's try this. Can you see that a little bit better? Okay, that's at -2. Okay, that's connecting to 1, 1, and then 2. All right, so that piecewise graph. So we are going to draw the derivative of that piecewise graph. Now, which means you're drawing the slope. How many different slopes are contained on this graph? There are 3 different slopes. There's a slope for the first horizontal piece, then there's a slope for the linear piece that's positive, and then the slope for the linear piece that's negative. So when you draw the slope, all right, your derivative for that first linear piece, what is the value of the slope? 0. So then your graph is going to go along 0 and end in an open circle. Anytime you come up to a corner, you need to have an open circle on your derivative graph. So for that whole section, the slope value is 0, so I draw a line that's worth 0. All right, the next piece, the positive linear piece, can you figure out its slope based on the numbers that I've given you on the graph? What does it rise over run? Okay, and so we're going to go up to the number 3, 2, 3. Open circle, because there's a corner, and open circle at the end. Oh boy, that's really tough. Yep, it ends at 1 because that's where the other one ends. And then what about the last little piece? What is the rise over one of the last tiny piece? Okay, the very last little piece between x's 1 and 2. What's the slope? -1, so I need to drop down to -1. Open circle, and I only end on a closed dot at the end because I'm not at a corner. Corners are open circles. Yeah? For the same, if you think about it as the run, the same length of the run of the left graph should be the same length of the run for the right graph. Yeah, because for my scale it was rise 3 over 1, so then I go and I do a thing that's up at 3, but I only go over 1 unit. And the other one was drop 1 over 1, so I went down to -1 and I went over 1. So it's always the same domain, which is the run value. Okay, for the horizontal piece, the rise was 0, but the run was, as long as the other one, so I made the other one, the rise is a value of 0 with the run length with an arrow on the end because it matches the other one. So you're going to try doing that a couple times. We'll get to how to draw derivatives of curved graphs. We're going to start with derivatives of straight graphs.